Hey, I'm okay. How are you doing? Okay. I didn't go to the thing today. I didn't know it was specifically cost team focused. I thought it was for everybody, so I was like, that seems like a lot of people. I didn't feel it, so I felt silly for not going. But I was here. It was fine. I don't know. Yeah. Okay. Are you staying awake? Are you leaving? You're running away now, huh? Yeah. Yep. All right. See you later then. Good seeing you. Yep. Yeah. Heard. Bye. No, we don't want that. Oh my god, no, not that. Oh, nothing. I'm just not doing this correctly. This needs to stop. I'm sharing this session unless you want to.
Okay, you can change the slides and stuff, right, Travis?
I can change the slides?
Yeah.
Sure. This is like in a scroll. That's right. That's what I thought you meant. Is like, oh, that's how you want me to change. Great. All right, it is scrollable. I I thought I would. Yeah. Shut up. This is so dumb. Pew, 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 pew. 2 minutes? Are you on the timer?
I'm gonna try.
Yeah.
I don't know.
Well, yes, we're going to do that.
Ambitious. Okay.
We're going to do that. We're going to give them applause at 2 minutes. All right. Well,
I feel like saying no.
could I have the flash talk speakers to the wall, please? Flash talk speakers to the wall. I think we want to give them that microphone.
Less than a minute.
Oh, really?
Yeah. This is actually.
Oh, it made a beep though.
It did make a beat.
Yeah.
Announcement?
No, we have a different slide actually. This is an updated slide that the speaker.
I think I took the last one.
Let's just show that slide and then
Yeah.
we move on to the PDF. If you go to the box folder
What is
which is on
Safari?
Firefox
Safari.
and participants material maybe.
Is this what we should be pulling presentations from?
But
Usually
yeah, that
we do it
is
from
why
there.
I took
Okay.
it. That is why I thought I got.
Are we getting questions
Sorry,
for?
I thought I got the last one because it was
So
there.
let's do go
We
for
are?
the
Oh.
box Thursday.
Or this section?
One that was asked.
More than our average.
Like when did you update this?
And
There. For us to just leave the mic on.
is the last one you sent?
Yes.
Okay. Can we just share
Okay.
these or should I download
We
these?
can share that and then kick to the PDF.
Let's just download this very quickly and then we can just show that. So if you go here, go to downloads. Yeah.
Hey, everybody. Welcome back. I am Travis Fisher. I will be your guide this afternoon. I'm an ESA or astronomer here at Space Telescope Science Institute. We're going to start off with our flash presentations. We're going to have everybody give their 2-minute spiel, and we're going to appreciate them for those 2 minutes. And if the timer goes off, we're going to applaud and say thank you, and we're going to move on to the next one. So there's a second microphone right here, right there, and then I think this one. Okay, I mean, yeah, use that one. Then you can pass it off as a torch. That's the baton.
All right. How close do I have to hold this? Okay.
All right, go for it.
Okay. So hi, my name is Allison Arena. I'm a PhD candidate at the University of Wisconsin-Madison, working with Christy Tremonti. Broadly, our current project focuses on understanding why massive early type galaxies exhibit such an abrupt cessation in star formation after an intense burst around redshift 3 to 5. We use the Hysea sample from Davis et al. 2023 as a more accessible set of nearby analogs. They are massive, compact starburst galaxies undergoing dissipational mergers. They're all around redshift of a half and are known to have extremely fast ionized and molecular gas outflows. So for this poster, we're focusing on our most dramatic source, nicknamed Makani. Its outflows are substantial, involving about a third of its total gas mass. The image on the bottom right here is from collaborator Dave Ripke and shows Makani in O2 emission with the HST image superimposed. And it's almost too small to see, but there's a very tiny circle at the very center in green, and that's the compact core of the galaxy. And so the question that we want to address here is, what is causing these outflows? So the two main culprits for such extensive galactic winds are an active galactic nucleus or stellar feedback. And based on previously acquired optical and UV spectra, an AGN is pretty unlikely, although wise color placement makes things ambiguous. For stellar feedback to account for what we see here, though, it would need to be contributing to the winds at suspiciously high efficiency. For our part, we use our recent MIRI MRS data to consider several AGN diagnostics, including strengths of forbidden neon lines, dust features, silica absorption, and comparison to empirical SED templates. Though it hardly ends up coming as a shock, we find little evidence of the presence of an AGN driving these outflows, and while stellar winds and supernovae are much more promising, it still doesn't provide a complete solution. However, this is still very much a work in progress, and I would be happy to chat if you have any questions or feedback. Thank you.
Okay.
All right, hello everyone. My name is Mason. I'm a graduate student at the University of Alabama, and I study how supermassive black holes grow when their host galaxies merge. The two ways this can happen are either through old-fashioned accretion, where one or both would show up as an AGN, or else through the direct merging of the two supermassive black holes in the merger. I look at both of those, but for the sake of time, I'm just going to talk about dual AGN. Dual AGN should be relatively common, especially at separations less than around 10 kiloparsecs, where they're predicted to be brightest. However, observations are actually pretty rare, depending on how stringent you are, maybe around 100, known as conservative estimate. So I am trying to assist with that, analyzing a data set of 282 late-stage mergers with predicted separations less than 10 kiloparsecs to quantify things like AGN frequency, stuff like X-ray luminosity in the process. Compare that to a controlled data set of non-interacting normal galaxies pulled from the same parent volume-limited sample of SDSS galaxies in order to make potentially a strong statistical statement about AGN or dual AGN triggering in mergers. If any of that was interesting to you, please come talk to me. Also, if you're interested in supermassive black hole mergers, I have stuff about that on my poster. Like I said, I excluded it for time. I went a little quicker than I thought I would. All right, thanks for your time.
Hi, I am Francesco Salvestrini, a postdoc at the INAF Observatory in Trieste, Italy, and I'm presenting the results of work about coevolution between star formation and black hole accretion in hyperluminous quasars at cosmic noon. These quasars are among the brightest objects in epoch where both star formation and black hole accretion peak, and so they are very interesting. And we need to rely on millimeter observation in order to study the properties of the host galaxies, which is not visible at optical or UV wavelengths because the quasar outshine the emission from the host galaxy. We use continuum emission to model the dust, the far infrared spectral energy distribution, and so we can measure the dust mass, the star formation rates, which are quite high, between 100 and 1,000 solar masses per year. And when we use the CO emission lines to measure the molecular gas, what we see is that the quasars, which are in red in the plot in the middle, are quite depleted for a given infrared luminosity when compared to sub-millimeter galaxies at the same epoch. And so maybe this is an evidence for the quasar feedback on the host galaxy, because the quasar is actually doing something to those galaxies, because for instance, as we can see from the CO sled, the quasar have a steeper CO sled, so the quasar is steepening. But most important is that those objects has the highest star formation efficiency over cosmic time, and in particular, the red one are similar to the brightest quasars at the epoch of ionization. So maybe they are hosted in very compact objects that are also start forming at with very high efficiency. And so, if you want to know more, you can chat with me. Thank you.
Hello everyone, my name is Yang Sun. I'm a grad student at the University of Arizona. So today I'd like to briefly talk about my recent work on a specific type of galaxy called pulsar-burst, whose is a very rapid transitioning and quenching galaxies between the starburst to quiescence, and their star formation is just shut down abruptly within 1 gigayear. So the interesting questions regarding to pulsar-burst galaxy is that even though their current star formation rate is very low, they still have a lot of CO gas reservoirs reviewed by radio observations. So we think the potential answers for this question is that maybe feedback is working on there. They can driven outflows, like directly escaping, removing gas from the galaxies, or they can trigger turbulence or heating up gas within the galaxy to suppress star formation. So in this work, we search for sodium doubly traced neutral outflows in the local post-starburst galaxy, and also extend to the whole evolutionary sequence from starburst to pulsar-burst and to quiescent from the Sloan spectra to test the evolution of outflow velocity over time. So the results I want to highlight here is that we do detect a significant outflow population in starburst and post-starburst galaxy, but inflow population in quiescence. And in the right figures, you can see that outflow fractions and outflow velocity decrease over time along the whole sequence, and also within post-burst phase is also declining with post-burst age. However, we also check the fate of those neutral outflows. Only a small number of them can really escape the galaxy. And we also find a strong link with AGNs for those escaping winds in this BPT diagram. So if you are interested in this work, please come to talk with me, and also my poster is over there. And thank you.
Hi everyone, my name is Arjun Suresh, and I'm here today claiming that radio AGN activity in the low redshift universe is not a direct function of star formation rate. Radio AGN feedback is frequently invoked in galaxy formation theories to suppress star formation at high stellar masses. But interestingly, there isn't a reliable, statistically robust determination of the relationship between radio AGN feedback and star formation rate, which is why we thought it would be interesting to study the relationship between the two properties. So to do that, we use the manga optical IFU catalog, and we match it to the first and NVS's radio catalogs. And we fit two models to the radio AGN activity. We allow the first model to depend only on the stellar mass of the host galaxies, and we allow the second model to depend only on the SSFR of the host galaxy. And we compare the two models. So on the left plot, at the bottom on the x-axis, we have stellar mass, and on the y-axis, we have AGN fraction. The black points show this very strong trend of AGN fraction with stellar mass, which our mass model reproduces very well in pink. What it also does well is it reproduces the trend against SSFR almost perfectly well. Bear in mind that the mass model has no input about the host galaxy SSFR, and it still performs so well. But the SSFR model fails to do the same against stellar mass. So from these two plots and a lot of plots in our paper, we conclude that radio AGN activity is not a direct function of host stellar mass. Also, this is my poster for the paper. You can scan the QR code for the paper where we show a lot more plots and hopefully more robust arguments. Also, don't miss this cartoon of a radio AGN saying that it doesn't give a frack about SFR. Okay, thank you.
Hello. Hello everyone. My name is Shenli Tang, a postdoc from the University of Southampton. And in this poster, I'm presenting a pilot study of observing the CO 221 emission lines of 5 dual quasars between redshift 0.4 and 0.8 using ARMA band 4. So why are these systems interesting? First of all, because they are well-defined mergers with multiple evidences, including the velocity offset and also the interacting features from deep HC images. The second, the black hole properties of these systems are available to us from the spectroscopy, as with one example shown below here, which means we can study the correlations between the black holes and their host galaxies in these systems. So as a main result from this study, we are reporting that these systems are typically associated with large molecular gas reservoirs with molecular gas mass over 10 to the 10th solar mass. And also, if we compare the molecular gas fraction of these systems with those of inactive galaxies, which is shown by the black line, and we find most of them are located between the star-forming main sequence galaxies and the starburst galaxy, which is the blue line. Of course, this is a biased selected system. These systems are biased selected. But what we can say is that in this merger stage, which means roughly 500 mega years before the final coalescence, we don't see evidences of quenching in sense of the molecular gas. So the problem is, when will they quench? And also, besides the total molecular gas amount, we find that the distribution of the molecular gas of these systems really show a diversity. For example, in some systems, we find the offset of the CO center, which is here. It's about 20 kiloparsec away from the optical center of the quasar, which might be evidence of AGN feedback. And also, there's systems we find the molecular gas are associated with both of the nuclei, but also sometimes it only associated with one of the nuclei. So what makes the difference of these things? So that is the problem. Thank you.
I think that's everyone. Let's give all our flash presentations another round of applause. And this is you. Yes. Okay, great. Yep. Yeah, this is right here. Yep, this is for you. This is for you. Can you say your favorite animal? Can you say it into the microphone?
Cat. Are we good?
No, there's a light on now.
Oh, now it is working. Okay.
All right, Marini Bianson is here to talk about the impacts of AGN feedback in a local galaxy, the case of NGC 7469 from the eyes of Webb NearSpec.
Okay, hi everyone. I'm Marina Bianchini. I'm a postdoc at University of California, Irvine, and I'm working with the GOES team. Oops, sorry. Yeah, with the GOES team that I didn't name everyone that is on the early release science team because it will be too many people. But I want to briefly shout out to Kirsten that is on the MIRI team that works here, and Torsten on the NearSpec team. So they were instrumental to building our Cycle 1, our ERS data analysis. And so briefly, before I get into the science, I want to talk about a little bit about the program. It is called the JWST Study of the Starbus Birth Age and Connection in Merging Lurgs. The PIs are Lee Armas and Aaron Evans, and we have NIRCam and MIRI imaging, plus NearSpec, integral field spectroscopy, and MIRI, medium resolution spectroscopy for 4 galaxies, and we published a bunch of papers. So if you are interested in any of in your favorite nearby luminous infrared galaxy, you can check those out. And here just nice HST images with the average NearSpec field of view overlaid to them, so you can see the very dusty regions that we pointed, but in this case, mine is the brightest one. That is called the NGC. Sorry about that. That is called NGC 7469. This is a NIRCam composite image of the galaxy. And we can see here nicely some of the information about it. It is very nearby. It is classified as a lurg. It has a very bright Cipher 1.5 nucleus and has some very nice starburst ring, as I'm showing here, that was detected in the past, but we detected again with MIRI. Here, just for scale, we are zooming in the very central region, and in the past, people detected outflows in O3 and also in Silicon 6. And now I'll be talking a little bit of the unexpected other outflows that we also saw for this galaxy. So before I get into NearSpec, I just want to again highlight how amazing MIRI is. So here is just a figure from the paper published by Lee Armas comparing the total MIRI spectra, the Spitzer, and then the nuclear spectrum also from MIRI, and we can see how detailed it is and how much more information we can get from the MIRI data. And now, if we move on to NearSpec, this is a figure showing what I tried to do as the ESA folks do for the outreach images, and I failed, but you can get an idea. So here in blue, light blue, is the NearSpec field of view, and then the circles, the blue circles show the extracted annular region where we got the blue spectrum, and the central part here is the nuclear spectrum. And you can see that we have a lot of information, and I'll just go briefly through some of that we selected to analyze in this work, but there is much more, as the CO2 ice over there, there is not that we didn't analyze, and there is also the CO band heads, and in 2 of the gradings that we didn't have the chance to analyze on this work, and very high ionization lines as well. So first of all, this emission line, the O1, that we used that to get the spatial resolution of the data, because it is a permitted line and it is not blended as the Paschen Gamma, Helion 1, or there is no other narrow component on top of it, so it's just the tracing just the BLR. So we got the very nice spatial resolution at the wavelength of this line. And then The other region is around the Paschen beta and iron 2 complex that we also saw sulfur 9. That is a high ionization line, but only in the nucleus. And we use these lines as shock tracers and gas excitation indicators. And then on this region that for folks that work with K-band data are really familiar with that, we analyze the Paschen alpha and some of the molecular hydrogen lines and the bracket gamma as well, also to get the gas excitation, but also the kinematics. And last but not least, the PAH and the aliphatic feature at 3.4 microns that I won't be talking about them, and I point you to Thomas Lai paper that nicely shows about path destruction and how the AGN environment can influence these features. And now I'm going into the near spec results, where I'll be showing these are the moment maps for 3 emission lines, the iron, Paschen alpha, and the molecular hydrogen. You can see the distribution between the molecular gas and the ionized species is very different. But I want to highlight one special thing, that is this dual spiral structure that we saw in Paschen alpha, and we were extremely puzzled about it because it was very weird to us. But we checked in Paschen beta, we see the same thing. In bracket gamma, we see the same thing. So we thought independently fitting the lines. So we thought that was real. And then we compared that with a work from Sandra Raimundo that she saw similar structure in Muse data for Mercurium 590, and she interpreted that as an inflow, as a gas inflow. So we modeled the velocity field of the galaxy, and even though the residuals are not strikingly high, the highest residuals are either in the farthest part of the field, or they coincide with the highest dispersions, highest velocity dispersions as indicated by the contours. So we calculated the atomic, the filling factor, assuming a bunch of atomic physics for that, and then we got a mass inflow rate that is 2 orders of magnitude higher than the supermassive black hole accretion rate, meaning that there is gas that is being deposited in the inner region of the galaxy. So, but there are many assumptions on the geometry of what is going on. We also studied the gas excitation, and we found very high excitation regions that coincide where the dispersion is higher, both in the iron 2 and the molecular gas, indicating a common origin for these 2 emission lines. Probably they are produced by shocks, because in the past people found east-west oriented radio jet that we interpret that it might be causing these shocked regions, or the shocks are causing the radio emission. We don't really know the full story, but so far we think that the radio jet is inducing something there. And interestingly, we also compared with this MIRI imaging work that claimed there is a very wide angle outflow, but we just see that the AGN excitation is just farther away than it's not really an outflow. But yeah, so the jet is not to scale, just to be clear. What about the outflows? We also found a very interesting outflow in Paschen alpha as well. So Paschen alpha is doing all the cold science in this galaxy. That is, as you can see, the dispersion is very, very high. And when you zoom in a region close to the nuclear spectrum, we can see there's 3 components. One of them, the widest one, corresponds to the BLR. The other corresponds to this compact turbulent outflow, and the other is the disk. So the this is the BLR. This agrees with previous measurement from H beta, which is good. But we also found this other extra component. And we measure a mass outflow rate that is quite low, with a very low power because this is moving at systemic velocity. So it's just a turbulent gas in the very center of the galaxy. So we think that the jet can be induced in this turbulence because we calculated the jet power. It is many orders of magnitude higher than the outflow power. So I'm also, before I leave you with my summary slide, I also want to do a brief advertisement for a cafe. I'm happy that I've talked to people and I've seen people mentioning the code in this conference, which is good. And this is something that was that in the ERS team had put up to do a tool to understand the pHs and the complex continuum from MIRI, and now it is out. As you can see here, there are two examples, the 7469, our favorite galaxy, but also a very complex, deeply obscure galaxy that it doesn't do it. The job is not as good as in this one, but it is returning the feeding, but it is much more complex. So if you want to check it out and use it to feed your favorite MIRI data, you can check the code and you can talk to me or talk to Thomas, that is the Dust and Cafe expert. And I leave you my summary. Thank you.
Thank you, Marina. What questions do we have? We have one over there, and we have one over here.
Why do you say that there is an outflow? Because it has the same position and shape as the broad component, of the broad line.
Because of the extension, the physical extension, the broadline region, by definition, is unresolved. So the other component, if I go back, I didn't put the plot here, but if you remember from the beginning, the other one, our spatial resolution is 0.14 arcseconds. And this extends, the radius of this is 0.6 arcseconds. So it extends beyond the BLR. So that's why we think it is an outflow. It is the only interpretation we came up with.
Thanks, Marina. Now that we have these mid-infrared spectra, which shows broad line regions from Paschen alpha and so on, you mentioned the full width of Hoffmax, but can we use it to calculate, say, black hole masses and potentially extend this to, say, type 2 targets where we don't see broad lines probably in the optical or so?
We actually, in the initial version of the paper, we calculated the black hole mass, but the thing is, even though we have very good resolution, we cannot do reverberation mapping or even do the dynamical modeling to get the near spec resolution is amazing, but it's not as good as getting AO from the ground to do this kind of analysis, to do that deep of resolution to get the dynamical modeling. And for reverberation mapping, I think it is kind of tricky yet to do this because we would need more epochs. And extending this to type 2 sources, I don't know, because the morphology of this source is very special. It is a very unique, you see the ring, you see the AGN face on, and you see all this structure clearly, you can clearly disentangle. If you're looking at type 2, you have the very dusty torus, and you also have probably a star formation region on top of that. So it would be more complicated, but we can try.
All right, let's thank our speaker again. Yes, I think so. Can you say your favorite animal into the microphone?
Corgis.
Yes. Perfect. Excellent. All right. Isha Nayak is here, and she's going to talk about resolving stellar populations in the nuclear region of NGC 4258.
Hi, everyone. My name is Isha Nayak. I'm an MPP fellow at Goddard right now. Before I begin, I want to thank the committee for letting me showcase this amazing data set we have, as well as the NIRCam pipeline team, observers, help desk for helping us out processing this data. So today I'm going to be talking about resolving stellar populations in the nuclear region of NGC 4258, which is close by AGN. So NGC 4258 is about 7.2 megaparsecs away and has a supermassive black hole in the center of 40 million solar masses or so. Here I show the HST optical observations of NGC 4258. You see the spiral arms and the dust lanes. Everything looks seemingly normal. All right, there. Sorry, I had a cool transition here. I really want to show that. Okay, so here is a 4-color image with HST still shown in yellow and Spitzer in red. So with HST and Spitzer, you still see these spiral arms and dust lane. The red points are possibly very old stars or very young stars. However, with X-ray observations of a Chandra and radio observations with VLA, you see this arc-like structure offset from what is the plane of the galaxy. And current theory postulates that some kind of AGN activity happened and possibly outflows happened at an angle that is offset from the plane of the disk. So we want to understand what's happening in the spiral arms. Why did this arc-like structure happen in this galaxy? And to do so, we have NIRCam observations of almost the entire galaxy. And with these NIRCam observations, we're interested in studying shocks, the ISM, as well as the stellar content within this galaxy. So shocks on a small scale can compress gas and trigger further star formation, and on a galaxy-wide scale, shocks can quench star formation. So with NIRCam observations, we can study what's happening on a local scale and galaxy-wide scale with a parsec resolution with NIRCam. So there's a lot of NIRCam filter options. We decided on these 12 bands. 6 of them are emission lines, and the other 6 are continuum emission for continuum subtraction purposes, as also sampling the spectral energy distribution of the point sources in our observations. So with only 28 hours, we were able to cover almost the entire galaxy and get 12 NIRCam filter observations. So these are the 6 emission lines that we targeted with NIRCam. Iron 2 at 1.64 micron traces high velocity J shocks. J shocks can trace shocks up to 300 kilometers per second and are likely due to AGN activity. We also have Passion alpha, bracket alpha, and molecular hydrogen, which trace recent star formation activity. With molecular hydrogen, we can also trace low velocity C shocks, once again, likely due to recent star formation activity. In addition to these lines, we have polyaromatic hydrocarbon observations of the 3.3 micron PA feature. These PA features trace recent stars, such as young stellar objects, as well as very old stars, such as asymptotic giant branch stars. We also observe CO in absorption. So here I'm showing VLA 4.8 gigahertz in the white contours, and in the blue I show our NIRCam continuum subtracted iron emission line. So, so here in the VLA, if you remember, this is the anomalous radio arc-like structure emanating from the nuclear region of this AGN. and this here is the spiral arm. So we see plenty of iron emission here in the southern anomalous arc, as well as in the nucleus. I've added on molecular hydrogen. So with molecular hydrogen, there's a lot of molecular hydrogen in the nuclear region. You see both the molecular hydrogen and iron 2 shock fronts. With Passion alpha, a lot of the Passion alpha is tracing the star-forming spiral arm up here, which is not surprising since Passion alpha is a tracer of recent star formation activity. We also have plenty of PA emission. There's PA emission in this star-forming arm, as well as extended PA emission around the nuclear region. And it's not surprising that we find PA emission in the nuclear region because once again, with this photo, this is the region that we're finding a lot of PA extended emission as well as PA emission in this star-forming arm. So one way to study an entire galaxy is to look at the stellar content of the galaxy. And here I show a color magnitude diagram with over 10,000 point sources that we've detected in multiple filters. As a reminder, I'm plotting F164N minus F212N. So that's the iron 2 versus molecular hydrogen versus F212N on the y-axis. So there's a lot happening. I'm going to go through all of these stellar populations that we see one by one, starting with the red clump sources. Red clump sources are low mass stars under 8 solar masses that have a helium burning core and a hydrogen burning shell. And all these low mass stars kind of ignite their helium burning core at around the same luminosity. And so we see this overdensity of points of red clump sources right here. Now, as the red clump sources evolve, convective layers of the core kind of extinguish the helium burning shell. And while the star is waiting for the hydrogen burning shell, and while the star is waiting for the helium burning shell to ignite, it kind of stalls momentarily, leading to this overdensity we see here, known as the AGB bump. Additionally, there are oxygen-rich and carbon-rich AGB stars up here. In addition to these older stars, we can also distinguish them from the young stellar object population. At distances of about 7 megaparsecs, we're not resolving individual young stellar objects, but rather young massive clusters. So these YSOs are young massive clusters, are infrared sources. They're very red, and oftentimes their spectral energy distribution peaks at far infrared wavelengths. So here I've switched up the color magnitude diagram just to plot out the differences. So here I have 164N minus F335, which is the PA feature, versus F335. And once again, the AGB stars are around here. Seeing where the AGB stars are in an RA-DIC coordinate, we find that they actually trace the PA emission features quite well. So here is the continuum subtracted NIRCam observations that we have of F335. And it's not surprising that a lot of the AGB stars follow the PA emission, since AGB stars are a major production, is where PAs are majorly produced. We're also interested in where the young massive clusters are located. So here are the young massive clusters. They are very red sources in color magnitude diagrams. And where are the young stars located? So there's a few scattered young stars over here, or young massive clusters, and there's a few in the nucleus, but a lot of them seem to be on the right-hand side here. And once again, perhaps that's not surprising because they would be located right here. This is the HST image, and so there's a lot of dust lanes, so it's not surprising a lot of star formation is happening in that location. So we want to find out what's so different, what's happening in the spiral arms of the galaxy that's not happening in this anomalous arc-like jet feature that we're seeing in radio and X-rays. So we try to look at what's happening in each different structure that we see. There's about 1,500 sources in this northern star-forming arm in this box right here, and I plot those sources in a color magnitude diagram. A lot of the sources in the star-forming arm are located where the AGB bump feature is in the CMD. There's also scattered young massive clusters as well as fully formed AGB stars. In contrast, this upper anomalous arc-like feature, when we plot the 1,200 or so sources on the same exact color magnitude diagram, we see that there's actually quite a few more red clump sources with other stellar features such as the AGB bump, AGB stars, and young massive clusters scattered around. So there is a difference between the stellar content of what's happening in this star-forming arm versus what's happening in this lower anomalous arc. Upper anomalous arc. All right, so as for the lower anomalous arc, there aren't as many sources in this region. When we plot the 67 sources in this white box here, we find that there's a few stars in the AGB bump and also AGB stars in this region. It could be because shocks, because we see the iron 2 feature here, are making it so there isn't as many stars forming in this region. Also, it could be that this lower anomalous arc is behind the plane of the galaxy, so it's heavily extincted and we can't pick out the point sources. So in conclusion, we have made observations with 12 NIRCam filters to detect the emission lines as well as the continuum emission. We want to characterize the AGN, the spiral arms, the anomalous radio arc seen in various wavelengths, and how shocked excited gas affects the current and past star formation. Initial results are that we have detected 129 young massive clusters and 189 AGB stars. And I do want to note that we got more data 3 weeks ago. So up until 3 weeks ago, this was our coverage that we were working with. And as of 3 weeks ago, we actually have a lot more data in the southern region over here. And we cover another spiral arm. It's a little hard to see around here. So we have a lot more data that we're excited to dive into this summer and publish papers. So this is my last slide, which I will leave up here as I take questions. This is such a rich data set that we not only see like the stars forming within this AGN, but everywhere we look is a deep field. Like there are so many background galaxies everywhere we zoom into. So yeah, I'll end there and take any questions.
Thank you, Isha. What questions do we have for Isha?
So do you think that the VLA data that you are seeing, it is associated with star forming regions? Is it jet from the AGN? What do you think? Yeah.
Okay, so the VLA data, we have 4.8 gigahertz and 8.4 gigahertz. So we can calculate the spectral index. So this is a map of the spectral index of the source. So the less steep is indicative of, so the yellow-orange colors is indicative of Bremsstrahlung radiation. And the more steep features, so the purple colors are indicative of more synchrotron radiation. So we do think there's star formation happening in this northern spiral arm. This upper anomalous arc is likely some kind of synchrotron radiation effects from the AGN. So you will notice that at the center here, it looks yellow where the AGN is, but it's actually not Bremsstrahlung. It's more likely stacking of several synchrotron emission leading to a less steep slope here, making it look like it's Bremsstrahlung radiation at the nucleus. And at the lower anomalous arc, it's a mixture of the two. So we're hoping to combine existing data with our NIRCam observations to further figure out what's happening where.
I had a similar question, but I think I would ask another one. So you detected some like shocks, right? Like iron 2 emission towards the center, but not coincident with the radio observation. Is that right?
So we detected iron 2 as well as molecular hydrogen, so high velocity and low velocity shocks. So the outline here is of the VLA observation, so it is coincident with the VLA
Okay. Yeah, I was wondering, like, you do not see the shocks kind of on the end of the radio. You kind of see it kind of concentrated on the center. So
Yeah.
why, I was wondering why that is. Like, I I think I would hope to see more shocks towards the end of the radio if it's kind of driven by the AGN.
So this is a single contour, and so if there were further contours, it would show that the iron tube is at brightest source right here. That's why we're able to see it coincidental at those places. So if we had more time, we could maybe see it in faint locations.
Got it. Got it.
A bit more technical, but like I'm not familiar with the near cam data. So like when you go through the filters, does the PSF change? And so how sensitive are your color diagrams based on this? If you had to make any PSF corrections or so.
So yeah, it does change. We convolved everything to our longest medium band filter just to get everything kind of pixel to pixel matched up so we can just divide things easier to make ratios. So it does change, and we use the web PSF tool to convolve everything to our filter choice to keep everything consistent.
Okay, great. Thank you again. Let's thank our speaker again.
Can you hear me?
Yeah, what's your favorite animal?
I'm too nervous for that.
Oh, man. You're gonna do great. All right, Elena Bertola is here to talk to us about the molecular view of AGN feedback at Cosmic Noon. Do AGN gas deplete their hosts?
Yeah, so hello everyone. I'm a postdoc in Florence, but this work was mainly done in Bologna during my PhD, and I'm very happy to present it because we finally managed to submit the paper 2 days ago. So referee, if you're in the room, please be kind, because this is a list of more than 30 people, and bridging all their comments and all their ideas and concerns was a pain. So first of all, why do we care about agent feedback? I think that Giovanni already said everything that could be said, but just to give you a little bit more context. So we observe these tight relations between the supermassive black hole mass and the properties of the host galaxies in the local universe, and what is putting them into place. And one of the answers, like the most straightforward one, is maybe coevolution between AGN and their host galaxies. And then we already seen different versions of this plot, but basically we cannot really reproduce the distribution of the stellar mass of galaxies unless we introduce both star formation feedback and AGN feedback. So the idea of investigating the molecular gas content of AGN host galaxies comes from the idea that if AGN and galaxies co-evolve, then the AGN is going to impact on the star formation, but then before impacting on the star formation, it might impact on the molecular gas, which is the fuel of the future star formation in the host galaxy. So basically, the question then becomes, do AGN affect the molecular gas reservoir of galaxies and then the star formation as a consequence? And I'm going to focus on the cosmic noon. This plot is not in this presentation because I was expecting it to be like everywhere, but basically cosmic noon is the peak of both the cosmic AGN activity and the star formation history of the universe. So it's where we expect AGN feedback to be at its highest. So what do we know from the literature about if AGN affect molecular gas reservoir of galaxies or not? Basically, it's a mess. So if you look at the low redshift, the answer to whether AGN gas deplete their hosts is no. If you look at high redshift, then the answer becomes yes, no, or maybe, depending on the works and the samples and the analysis that was carried out. And here is a non-exhaustive list of all the references, and also I invite you to check out Francesco's poster to get a little bit more insight in this. So gas depletion at redshift above 1, basically, as I said, is controversial, is a mess, and one of the reasons for this mess is basically that different works have different selection and they carry out different analysis. And here is basically a summary of all of the AGN that were studied up to 2018, broken out into volumetric luminosity and redshift. And as you can see, in the low redshift universe, they are spanning a wide range of volumetric luminosity, while the yellow points, which were all the observations until 2018, were basically only covering AGN that are very high in power, so volumetric luminosity above 10 to the 46. So to bridge basically the volumetric luminosity range spanned by lower redshift and local universe AGN and the higher redshift, these two surveys, SUPER and CASH-Z, were conceived. So basically their aim is to assess the presence and the effects of AGN-driven winds in the ionized gas component in AGN that are selected only based on their X-ray luminosity from deep and shallow fields, so that we can nicely span a wide range of power in volumetric luminosity. And as you can see here, they have different selection criteria based on how the observations were conceived. And one of the most interesting results from these surveys was this result from Circosta 2021 with the SUPER survey. And basically what Chiara saw is that when we include more regular AGN, then we don't really see gas depletion at its highest, and maybe so we only see hints. And their conclusions were that maybe gas depletion is not really significant, or maybe we need bigger samples. So, oh, sorry, I forgot this was here. And then we have another issue, which is simulations. We heard a lot about this, but basically results regarding AGN feedback in simulations, in cosmological simulations, is simulation dependent. And usually AGN are seen as not more gas depleted than regular galaxies. And this is probably due to issues in the simulations on how, or on the benchmarks that we are not giving to the simulations as observers. So basically what we did was to increase the sample size of AGN and cosmic noon studied for their molecular gas reservoir by bridging, putting together CASH-Z and SUPER surveys. So this is just like the updated version of Circosta 2018 with the full CASH-Z sample. And here you can see the two surveys broken out in X-ray luminosity against redshift and volumetric luminosity against redshift. And in the lower panel, I'm only showing the AGN that actually made into this study. So basically, SUPER and CASH-Z AGN that were actually targeted by ALMA. And as you can see, there's quite a difference between the upper and lower panel in the CASH-Z, and that is because we took ALMA archival data and not ALMA targeted observations. So basically, we put together SUPER AGN, which were targeted by a dedicated ALBA program targeting CO322. Then we mined the ALMA archive for all the observations covering CO emission lines at J below 4 of CASH-Z AGN. And this basically adds up to almost 50 AGN that were targeted by ALMA in the two surveys. Then we ran dedicated SED fitting with the most updated catalogs from Cosmos and GOODS. And we also updated the SED fitting or SUPER AGN based on this updated photometry. And only 6 AGN were so bright that we could not measure the stellar mass from SED fitting, so we had to discard them from the sample. Then the idea of this work is basically to compare AGN to non-active galaxies. And to do that, we build a control sample of non-active galaxies by matching our non-active galaxies to our AGN hosts in redshift, stellar mass, and star formation rate. And we do that in two redshift bins to take into account also the evolution of the main sequence in redshift. And another approach that we use that is, let's say, common in in this kind of studies is to rely on directly measured quantities and not convert them into physical quantities so that we have less assumptions. So this is our proxy for the molecular gas mass, this is star formation rate, and this is gas fraction. And here is the comparison of our AGN and non-active galaxies. So this is crowded, sorry about this, but basically what we did is that we compared AGN and non-active galaxies in gas mass against star formation rate, gas mass and gas fraction against stellar mass, and then gas fraction distribution. What we see is that at fixed star formation rate, so far infrared luminosity of the galaxy, the difference is 3 sigma. This difference for fixed stellar mass is reduced, but then, as Giovanni spoiled in his review, we see that the gas fraction distribution of AGN is significantly skewed to lower gas fractions, even though the mean values of the two distributions are consistent one another. Okay, and then we also compared our results with cosmological simulations. And to do that, I forgot to write it, but yeah, basically you have it here. We use Illustris TNG 100, Eagle, and Simba. What we did was basically to take the output of the simulations, and we filtered the output so that AGN and non-active galaxies of the simulation were resembling the observed samples that we had. So basically, we selected the same range in star formation rate and stellar mass of the snapshots at redshift 2, and then we identified AGN as those galaxies hosting an AGN with volumetric luminosity higher than 10 to the 44 and highly accreting. However, if we reduce this threshold to 10% of this, so it's 10 to the minus 3, results are unchanged. So what we see here is basically the same comparison. Oh, and also these plots assume alpha CO 3.6, and this black line arrow is basically showing the shift if we would have assumed alpha CO 0.8. So basically the two values, like the two bounds of the range of alpha COs that were measured. Here you can see the comparison of molecular gas mass against star formation rate for TNG, Eagle, and Simba. The smaller points are our observed targets, while the triangles are in blue the binned non-active galaxies from the simulations, and in red the binned simulated AGN. And as a color map underneath, you can see the distribution of AGN host galaxies with a color coding that is the mean of the stellar mass in that bin. So basically what we see is that the simulations are not really predicting AGN to be gas depleted. If anything, they have the same gas fraction, the same stellar mass, molecular mass, sorry, in the simulations. And also, they are not really reproducing the right range for AGN host galaxies. And then here we see the gas fraction against volumetric luminosity. The gas fraction basically depends on the alpha CO value, but then the simulations are missing the high volumetric luminosity AGN, which is something that we already knew. But then this is what I find most interesting. Here is the gas fraction distribution in simulations, and in black you see those from the observations. Dashed is non-active galaxies, and solid is AGN. And as you can see, the simulations basically predict the opposite trend if any difference is present. So basically, AGN are not more gas depleted than non-active galaxies. And I'm going to leave you with my summary.
What questions do we have for Elena?
Thanks for your talk. So when you're calculating the molecular gas amount, are you assuming the same conversion factor of from CO322 to CO120, then also the conversion factor from CO to molecular gas? Are you assuming the same factor for your quasars and the galaxies?
So we're not assuming the exact same values, but we're taking the CO SLED for AGN from Kirkpatrick 2019, and we're considering their scatter as error bars, which are kind of wide, which is also why we have, let's say, the some error bars in CO are quite broad because the scattering SLED is dominating. However, the SLEDs that we assume for AGN and non-Arctic galaxies are consistent, so we are not really introducing differences based on the SLED.
Okay, so since I think the ionization environment of AGNs are more complicated, so I was wondering if this skewed distribution of the LCO120 of AGN compared to the non-active galaxies is just a skewed distribution of those conversion factors.
No, it's not, because this skewed distribution basically comes from the upper limits. If we take the upper limits in CO from this distribution, basically we don't see like this skewness anymore, and also the CO detections are what are driving the mean value of these distributions. But then if the CO SLEDs are kind of like they're compatible, then we should not be introducing any difference in that.
I see. Thank you.
Are there any further questions? Okay. Well, let's thank our speaker again. Thank you so much. And then I think she's... Yeah, perfect. Hey, come on over here. Yeah, Miriam Eliezer is here. We're going to be talking about MIRI MRS insights, unraveling the kinematics of luminous infrared galaxies at Z of around 0.6. Can you say your favorite animal real quick?
It's my cat.
Yes,
His
excellent.
name's Finn. All right. Is there a way to... That's okay. Okay, wonderful. Thank you so much. Hello, everyone. My name is Miriam Eliezer. I am a second-year graduate student at the University of Massachusetts, and I'd just like to take a moment to thank my research advisor, Professor Alexandra Pope, as well as all my collaborators who have helped me out as I've been working on this research. So today I'm going to be presenting the findings of my research, which is on the kinematics of luminous infrared galaxies at a redshift of 0.6. So luminous infrared galaxies, or LIRGs, have an infrared luminosity of 10 to the 11 to 10 to the 12 solar luminosities, and they're powered by a mixture of intense star formation and AGN activity. If we look at these LIRGs in the local universe, they appear to be triggered, the intense infrared luminosity appears to be triggered by pretty much exclusively major mergers. But if we rewind time 10 billion years ago, we can see that they appear to be more similar to local star-forming disks, like that example over there. So what will we see if we look at the kinematic signatures of these luminous infrared galaxies at intermediate redshifts? Will we see signatures of rotation, or mergers, or something else entirely? So this example is from SDSS Manga, but in order to investigate this question, I used MIRI MRS data that was taken as part of the Halfway to the Peak program, as discussed by Jason Young, who presented earlier. So as you can see from the plot on the right, which I'm sure you are all very familiar with, the cosmic star formation rate peaked at a redshift of 2, but by the time we get to a redshift of 0, that has dropped by over an order of magnitude. So the Halfway to the Peak program aims to investigate what could be causing this decline by examining a sample of galaxies that are at a redshift of 0.5 to 0.6. So this data set was also leveraged existing Spitzer IRS data that in order to get a sample that ranged, that spanned a range of star formation dominated to AGN dominated systems. This is also at a time when we have a rich suite of diagnostic spectral features that are visible in the mid-infrared, which is wonderful because it provides us with a robust tool to analyze these data while mitigating the impact of extinction. And the MRS data also affords us the resolution to be able to track the changes in the spectral line profile spatially across the galaxy. So down here, I'm showing white light images of our sample, and that basically just means they're the Miri MRS cubes that are collapsed along the spectral axis. And they're ordered in their AGN fraction from the lowest AGN fraction over here to the highest AGN fraction over there. And if you place an aperture on these images and that captures all the light from the galaxy, you can extract a spectrum that looks like this. And here at the top, I'm showing FLS1, which is one of our more star formation dominated galaxies. It has an AGN fraction of 23%. And down here at the bottom, I'm showing FLS6, which is one of our more AGN dominated galaxies, which has an AGN fraction of 88%. And I've just highlighted the lines that I'm going to be investigating. So it's argon 2, neon 2, and those are both star formation tracers. And then I also looked at H2S5, which traces warm molecular hydrogen, which can be indicative of shocks. And if we zoom into the argon 2 line here, we do see something interesting already popping out, which is that these spectral lines are double peaked. And we do see a bit of a difference between our more star formation dominated galaxy and our more AGN dominated galaxy, where the more star formation dominated galaxy does seem to have a broader double peaked feature. All right, and we see that this holds true pretty much for the rest of our sample. So this is the argon 2 line for every source, and these are just overplotted on the same plot with the flux density normalized to 1. And we can see that the more star formation dominated galaxies do have broader features here. So this is great. We get a kinematic signature, but unfortunately, this doesn't really disentangle whether this means that these LERGs are more disk-like or if they're more merger-like, because you can get a double peak spectral feature from either one of those situations. So in order to investigate this further, I made some kinematic maps, and I basically just did this by using QViz to extract a spectrum from every spaxel. Then I wrote my own code to isolate the line of interest, fit the continuum, fit the line, make sure that the signal to noise is quantified for every single spaxel. For the spaxels that were below 6, we just disregarded those. But for above 6, I just went ahead and investigated those by eye to make sure that the fits were good before including them in our analysis. And the results of those efforts are shown here. So this is the argon 2 velocity map for FLS3, which has an AGN fraction of around 70%. And down here, I'm showing you the size of the PSF. And then I've highlighted some of these boxes right here, which the area of which is greater than the size of the PSF. And then I summed the spaxels inside of here, normalized them to 1, and I put them in this side panel over here just so you can see that they're consistent with the velocity gradient that we're seeing here, and they are resolved. Wonderful. So I went ahead and did this for the whole sample. And I know this is a little bit busy, but I'll just break it down for you real quick. These, each individual source is in its own box. And then we have 3 columns for each source, which is the signal to noise map here, the velocity map here, and then the dispersion map here. And I've also put the size of the PSF for all of these as well. And the thing that we find pretty interesting is that regardless of its AGN fraction, we do see pretty prominent rotating disk components in all of our sample. Another interesting thing that that sort of pops out is that some of these galaxies have higher dispersion in the center, and it's good to note too that these are not, these color scales are set to where you can compare between the sources. They're not optimized to look at the differences in each source. But some of these do have broader spectral lines in the center, and that could be indicative of maybe like AGN feedback or the growth of a stellar bulge, but we're going to need HST images in order to confirm that, which we have applied for, so stay tuned. Maybe there'll be more about that in the future. All right, and I did do this analysis with 3 different spectral lines. So at the top, I'm showing the argon 2 again, and this is just for one source now. So this is for FLS1, which is our more star formation dominated galaxy. In the middle here, I'm showing neon 2, and then down here, I'm showing the H2S5. And basically what this plot tells me is that this trend we see for this disk component is consistent throughout all the spectral lines that we analyze. All right, so what I learned from this is that we do see signs of rotation in all these galaxies regardless of AGN fraction. So, and also they're consistent across all 3 of the spectral lines that we analyze. So this suggests that major mergers do not dominate these luminous infrared galaxies at a redshift of 0.5, the ones that we examined. It was just a really fun, it's been a really fun project to work on because it's one of the first times we've been able to use mid-infrared atomic lines to measure velocity maps of distant or at least beyond the local universe galaxies. But there's still a whole lot of work left to do. So one of the things that I'm working on right now is making these velocity and velocity dispersion curves. So this is preliminary work right here. And trying to quantify the signal to noise to see if these disks are stable. I'm also trying to quantify the velocity and dispersion in the central regions to see if I can infer velocity components for a stellar bulge or AGN feedback. And then I'm also going to be digging into the velocity properties of the higher ionization potential lines to see how the AGN might be affecting the kinematics of these galaxies. And look for any evidence of outflows or any other kinematic signatures. And with that, I guess I really sped through that. So I think that's pretty much all I have for you today. I'll end there. Thank you.
Okay, what questions do we have for Miriam? Oh, me, this guy. Hi. So, Travis, your maps were all really beautiful. This was a really great presentation. So when you had all of your individual targets and you're showing your rotation curves here, you noted that the nucleus had a higher full width half max. But looking at this one and then all of the other ones, it also could be interpreted that you're measuring the lines to have high full width at half max along the minor axis of all your measurements. So what could be happening there that we're seeing that's occurring?
So I don't exactly know yet, which is why I have the second bullet point here that I want to investigate a little bit further. Another thing that I'm actually going to be looking into doing is making a model of the rotating disk and then subtracting that out to look at the residuals to see what else might pop out there. So hopefully I'll be able to disentangle that a little bit further as we go on. Yeah.
Hi, thanks for a very nice talk. Apologies if I missed it. Could you say a little bit more about how you quantify the AGN fraction and how that kind of correlates to the strengths of these, the relative strengths of the 3 lines you looked at?
Sure. So that work was actually done by my advisor from the Spitzer data quite a while ago, but it's basically taking the PAW measurement that they get from the Spitzer spectrum and then decomposing the entire spectrum that they get from Spitzer and then taking the PAW component and the AGN component and computing it that way. But these calculations were redone using the spectra that we got from MIR-EMRS, and they agree within 10%. So.
So you have molecular hydrogen lines and you've got these low ionization lines. Do you have plans to assess the relative importance of shock excitation in these galaxies and whether that might affect any of your analysis, or if your analysis of this disky rotation might be related to that or not.
I hadn't really thought about it yet. But yeah, that is definitely something that I could do and we'll be looking into. Yeah, I could talk about that.
Very nice work.
Thank you.
I was wondering, so I might have missed this. What is the spatial extent that you're showing there in like physical scales? And also, like, if you don't see rotational, if you just see rotational profiles, it doesn't necessarily perhaps exclude the fact that there are no mergers there, because even in very low redshift targets, we do see in some ionization lines or so where it's perfectly rotating, but they are actually major mergers, and the emission is purely coming from the central nuclei. So I was wondering, like, if you have like other images like in other bands or so. I'm sorry if I missed this.
Yeah, no. So yeah, that's actually a really good question, and it is something that we're working on. We do have HST images of some of these galaxies, but there isn't there isn't a consistent, concerted imaging effort that's happened yet, although it has been applied for. So that's something we're still working on.
Any further questions? All right, let's thank our speaker again. Yeah, let's thank all of our speakers again. What a great afternoon session. Thank you. And I think we're moving. There was a last speaker because I didn't. Oh, you guys, bonus content, extra innings. This is awesome. All right. Yes, come on down. We're going to talk more. Okay, and this is you.
Yes.
Okay. Letizia.
Yeah.
Bujani?
Yes, Bujani.
Bujani, great. Letizia is here, and she'll be talking about AGN feedback in quiescent galaxies at cosmic noon. That's right.
Okay, yeah.
Your microphone works, so you don't have to list a favorite animal.
Okay, great. Nice. Okay, hello everyone. I'm Letizia Bujani. I'm a first-year PhD student at University of Bologna, and today I would like to talk about what we found in this sample of quiescent galaxies at cosmic noon by looking at their ionized gas emission. And these results are part of a wider research called the Blue Jay survey, whose members are here listed. So we have talked all week about star formation, but I'm actually more interested in the dark side of that, which is the quenching, specifically quenching in massive galaxies. So we know that star formation is tightly linked to the gas cycle inside and outside of the galaxies, and there are many steps in this cycle in which we have different modes of quenching. So studying the gas emission, especially massive galaxies, is crucial if you want to understand what caused their star formation quenching. It has been talked about a lot today, but we see a discrepancy between the dark matter halo mass function and the stellar mass function in galaxies. And of course, at low masses, we think that is mostly due to star formation, but in massive galaxies, it is kind of still a mystery. So we think that it may be due to feedback from AGN, but also maybe as a consequence of gas-rich mergers. And from the point of view of cosmological simulations, we have seen that the feedback from AGN, if implemented, can nicely reproduce this curve at high masses. But observationally, it is quite difficult to observe the direct link between AGN feedback and the quenching of star formation. So data comes from the Blue Jay survey, which is a Cycle 1 JWST observational program, which targeted 151 galaxies, all at redshift around 2. And in the Cosmos candles field, here you can see the pointings. And here you can see an example of one spectrum that we get from the MOS data. As you can see, I had to cut actually the spectrum because it would have gone longer. And we can see some nice absorption lines from which you can fit the stellar continuums. But we can also see some absorption lines from the neutral gas, of which I will talk about a bit later. And what's interesting me is emission lines from ionized gas, actually. So in order to isolate the emission due to the gas, we first have to fit the stellar continuum. And this was exceptional work done by a PhD student at Harvard, Min-Jung Park. And actually her paper is going to be published in the archive in the next few weeks. So look out for that. With using Prospector, we can fit both the photometry and the NeoSpec data, and we can get very nicely reconstructed star formation histories and a lot of stellar parameters. This is how we selected our quiescent sample. We get the star formation rate from the Prospector fits, and we select a sample of 16 quiescent galaxies found in the Blue-J catalog that have star formation rate that lie more than 1 DAX below the star formation rate main sequence at redshift around 2. This is some example of the mission line fitting from the continuum subtracted spectra. And as you can see, the first surprise is that we can see actually a lot of emission lines in these galaxies. And actually, only 3 galaxies out of 16 do not have any detected emission lines from warm ionized gas, which means that there is actually a widespread presence of ionized gas in these galaxies. The second surprise, kind of, is that we were able to fit so many lines that we could construct BPT diagrams of the whole sample. And as you can see, most, apart from 1, galaxies in the quiescent sample lie on the AGN side of the BPT diagrams. These are the other 2 BPT diagrams using sulfur lines and O2 lines. And this is another less known diagram that uses only N2 over H alpha and the equivalent width of the H alpha. But the take-home message of this is basically that we see a hidden population of AGN that were never detected before in this sample of seemingly normal quiescent galaxies. Actually, we see that 56% of the sample can be classified as AGN host. And this is really thanks to the new data from NeoSpec, because here I have a comparison between similar catalog of quiescent galaxies observed with Keck-Moss fire, and this is a stack of 18 of these galaxies, and you can barely see the H alpha and N2 lines, and this is one of the lowest signal-to-noise ratio galaxies that I have in my sample. So you can really see the difference that the James Webb data makes. And of course we check that these are actually quiescent galaxies using a star formation rate from the H alpha line luminosity, and they are actually quiescent galaxies. So this means that we found a lot of AGNs. Not only that, but we found also multi-phase gas outflows in a subset of these galaxies. Here I have 4 galaxies in which we can fit an outflowing component in the ionized emission lines. As you can see, these outflowing components are very powerful, and not only we can fit ionized outflows, but we find also that all of the quiescent galaxies that have ionized outflows also have neutral outflows, and this was analyzed by Dr. Rebecca Davis at Swinburne University in this exceptional work that you can already find on the archive. And we also found that 2 AGNs have only neutral outflows detected. One particular galaxy of this is exceptional. This is Cosmos 11142, and this is one of the galaxies that is actually a post-starburst galaxies, as you can see here from the star formation history that was reconstructed from Prospector. And in these galaxies, the ionized and neutral phase outflows were so exceptional that we were able to get the mass outflow rate both in the neutral phase and the ionized phase. And if we compare the ionized phase mass outflow rate, it is not really able to explain this drop of star formation rate in this galaxy. But if we get to the neutral phase, which of course brings out way more mass than the ionized phase, we can see that these two quantities are comparable. So actually the outflows that we see in these galaxies are able to quench the star formation in this galaxy. So, and this is of course an AGN, actually a Seyfert galaxy. So this is direct evidence of star formation quenching that was induced in this galaxy by powerful ionized and neutral outflows. Oh yes, and you can see here all of the, this is a paper by my supervisor about this particular galaxy. Lastly, this is something that I'm still working on. Of course, 11142 is the most exceptional cases of these galaxies, but I have many of galaxies which have similar conditions. So I'm trying to find a link between their star formation quenching and their AGN activity. So none of these galaxies are detected in the X-rays, and actually only one source is detected in the radio. So if we get the volumetric luminosity from the O3 emission lines and the Eddington luminosity, we can see that they are probably AGNs with a low Eddington ratio. So they may be low luminosity AGN that are inducing ejective winds in these galaxies, and what we see is the result of their star formation quenching due to AGN activity. I actually sped through that as well. So these are my main conclusions, that we see actually population of AGN which has not been detected by any other means at cosmic noon. Also, a subset of these galaxies have powerful ionized and neutral gas outflows that can be explained with AGN feedback. And so putting together these two findings, we can say that star formation quenching in these galaxies was probably induced as a consequence of AGN activity. Thank you. If you have any questions.
Question right here.
Hi, really nice talk. So you have detected like ionized gas and neutral gas outflow. So have you looked with molecular gas and see if you have detected any of them?
Well, we have we have asked for ALMA time. Actually, last year for only 11142, but it was not accepted. So we're trying again this year with more galaxies in the sample, and we hope we get some data in the molecular side. Thank you.
Hi, really nice talk. Could you talk a little more about the, when you went to then check, say, the star formation rates, you have this H-alpha line, but now you have AGN and star formation, decomposition that you have to do. So I was just wondering how that was done.
Yeah, well, we actually didn't do any decomposition. We didn't try because already just using the H-alpha lines for most of the sample. Here I have put like this black contours around the AGNs, and you can see that even though they probably have most of the H-alpha emission coming from the nucleus itself, so not star-forming regions, we still find them to be quite lower than the star formation rate the star formation main sequence, which is this line here. So we think that not only these are a kind of low power AGN, but they are really quiescent galaxies.
Thanks.
Could you please talk a bit more about the demarcations on the BPT diagram that are used to separate AGN from star forming, and if they're valid at even higher redshifts?
Yeah. Yes, yes. Okay, so let me see if we get, okay, yeah. I have put here, okay, this is my catalog, but here in gray is the SDSS catalog at redshift around 0. So we can see that also the star formation sequence is actually kind of shifted, but this is a known phenomenon that is observed with galaxies at cosmic noon, since the ionizing flux should be a bit higher. So this is all shifted. But still, we're outside this line here, which is the theoretical maximum starburst line, over which you cannot, at least with theoretical calculations, you cannot explain the line ratios that you see by only using a star formation in a galaxy. So I think these are actually pretty solid results. Of course, this demarcation here between Seyferts and liners in the BPTs is debated. So some of them are actually kind of in the liner regime. And of course, we have not talked about shocks, but that's also something that we could get into.
You have one more question?
Thanks for the great talk. I was just wondering, do you have any kind of feeling of what the multi-wavelength information of these objects look like, for example, in like the X-rays or the radio, that could help you feel more like you put even more confidence on the fact that, you know, these are definitely AGN contributing to these conclusions, and I think it could be backed up by multi-wavelength information?
Well, yeah. In regarding the X-ray data, I have looked, of course, but the problem is that for Cosmos surveys, there are some X-ray surveys, both from Chandra and XMM, but they are not that deep. They are not as deep, for example, as the Chandra Deep Field survey. So I have actually calculated what X-ray flux they would have at this bolometric luminosity, and they all fall under the sensitivity of both Chandra and XMM. So either deeper X-ray data, which would be nice to have. Of course, we have put in the request for the ALMA data, which we hope that will be okay. And then in the radio also I've checked, but they are not really detected, so maybe also deeper radio.
Yeah, is that through VLA Cosmos by any chance?
VLA Cosmos doesn't detect. It detects only one of them, which is actually this galaxy here, which is almost at the highest Eddington ratio. So maybe far infrared data for.
Cool. Sounds great. Thank you very much.
Let's thank Letitia again.
Thank you.
Thanks. You can just put it right there. And apologies for cheering before you were able to give your amazing talk. So that is, I confirmed, the last speaker for today. So a couple quick announcements. From yesterday for SDAS, we have leftover beverages, so we invite you to join us back in the cafe to enjoy them until 6 o'clock. While you're doing that, poster screens are going to be active until 5:30. So if you want to make sure that people come and see your poster and talk a little bit more about your amazing science, you have that opportunity. And then after 6, we are meeting at the Colonnade, the Inn at the Colonnade, for dinner at 6:30. So we are looking forward to seeing you there. So thank you very much. This has been Thursday for our One Amazing Conference. Thanks, everybody.